Huckabee Random Clock Talk. This is tape number 11, and we're looking at a clock movement here that is unusual, and most clockmakers will probably never encounter a movement of this type. This is a massive movement, being about near 10 inches wide, about 9 inches high up the frame of the movement, and about 8.5 inches deep. This movement was built by IBM and is one of the last movements that IBM built, the last model and the last movement that they built before disposing of the time equipment division of the company in 1958. This movement was approximately the masterpiece of the company. It was placed in a case about 5 feet tall by about 18 inches wide, about 9 or 10 inches deep. It was used as an industrial time control to provide time for various industrial devices, and we'll discuss the features on this as we go through the unit. It has a sweep second hand, this large black disc in the center of the dial, the red sweep second hand. I do not have the minute and hour hands for it. There's quite a number of features that we'll mention, which I also do not have. I worked for IBM for 38 plus years, being employed in the time equipment division immediately after World War II and continuing there until my retirement in 1986, in the spring of 1986. This particular clock is one of the types of movements that I worked on day by day. We mentioned in the earlier part of the tape an industrial time control, a balance wheel movement, and discussed that it was capable of about plus or minus 30 seconds per year accuracy. This movement here, and the clock that this went into, had a time capability of plus or minus 1 second per year. 1 second per year. That is an astounding degree of accuracy, and as we look through the movement, I'll discuss how that was obtained. Turning this movement over, looking down here, we see the crutch that when coupled up to the pendulum. That crutch is bent forward here so that I can stand the movement on its base. But when this is down, this crutch straddled the pendulum rod. Note that the breadth of that crutch fork is approximately the same as this number 2 wood pencil. As we turn this around, and one of the features that I do not have on this is a stud that passed through this hole, stood out into the opening in this region, and that stud supported the pendulum. The pendulum for this unit was used a 1/4 inch diameter Carpenter 37 N-bar rod, which is the most dimensionally stable piece of material that is ordinarily available in the world, even till today. That rod supported the pendulum. The ball was supported in the midsection, and the pendulum itself was temperature compensated to the very highest degree of precision that the industry knew at that time. In the service of this unit, there's a couple of screws back here in the back on the cast iron frame. We'll slip a couple of these screws out, and I'll show you a feature of the mounting means. And on the regulator clocks that I have built in more recent years, and as recent as just this past year, I have made every unit with this feature somewhat copied from the IBM principle. You notice the cast iron back frame that's mounted in the rear of the clock. The pendulum stud that supported the pendulum went into this hole, and the movement can be slipped off and removed for service without any disturbance to the pendulum whatsoever. This was a feature that was developed in the IBM philosophy that was developed in the IBM clock master clocks, and it dates all the way back to some of the earliest movements that we built. And incidentally, the roots of IBM goes back to the W.L. Bundy time recorder company and the Day dial recorder company, D-E-Y, Day, that go to just a few years, 2 or 3 or 4 or 5 years before the turn of the century. Actually, clocks and timekeeping was the basic business that ultimately became the gigantic IBM as it's known today. I have a few mementos that when I retired from the company that I retained. This particular pencil here is one that says IBM number 2 on the pencil. This particular little block here that I use for a bench block in the business has an IBM part number on that end and another on this end. And if we take a look in the front, right in this area, you can see the mathematical sign minus, the mathematical sign plus, and there's a little inscription there. If we turn it over, we see the same thing in the other side. What this is a die that type bar type heads for the typewriter business in IBM is made with. This is extremely hard steel, and the slug, the type slug that's on the end of the type bar, the IBM typewriter, was struck into this slug to get this impression. This was a special character key. This is, if we look at it this way, is minus over plus. That is, in the typewriter you would have a key that in the uppercase would be a minus and the lowercase would be a plus. If we swap ends with it and take a look at it, we find it's a plus over a minus. In special keys, we had minus over plus and plus over minus as the customer might like. This is one of the hardest pieces of steel that you will ever encounter, highly finished. That's a memento from the companies, beside the point of the clock movement. Let's turn around and look on the back side and see what we have in the movement. See if I can get this in the light. You see the plate is rather massive here. The crutch is turned over for the reason that I mentioned a little earlier. This is the Escapement Anchor bridge on the back side. These studs, these 2 studs here are purely stops against the back plate, and the tangs on this one and this one is the one that locks the movement into the back plate. Let me point a characteristic of this movement. If you look at this appears to be gold in the, or gold colored in the tape here. And let me tell you of a surety, this is real gold. This is real gold here. This is very heavily gold-plated. There are certain areas of the movement that appear to be, that have the same appearance of the gold color, which are not gold-plated. For instance, the crutch right here. This is not gold-plated. That is brass. If we look at the stud down here and up here, this is gold-plated. This attachment plate that carries some contacts over here is not. The attachment plate here, carrying contacts in this region, is indeed gold-plated. And we might ask, why the mix? Why the mix of parts that are gold-plated and parts that are not gold-plated? Well, in the finest movement that IBM built, all of the brass parts were gold-plated. All of the steel parts were blued. As the movements were lesser dear or lesser precision and whatnot in the marketplace, we used similar pieces, similar parts. A lot of them were, there was a commonality between the pieces that we used, and they were not gold-plated. This particular movement is probably one of the last movements that IBM ever built in their plant in Endicott, New York. The reason that I say this, it was a common situation in the company to stamp the manufacturing date right down here. This particular movement says October the 2nd, 1957. And oddly enough, on November the 1st of 1957, IBM announced the disposal of the Time Equipment Division. So this movement was built something like the last month of the manufacture of IBM's time equipment devices. Well, how did I get the gold, not gold situation? In the disposition of all of the parts, pieces, and scrap and whatnot that was in the company, I realized in that period of time that the history of this would go by the wayside very quickly, and there wouldn't even be a trace of the pieces left. So I set forth in the scrap bins, the reject parts, spare pieces and whatnot that was in the final closeout of the remnants of pieces to try to gather together enough parts to assemble an entire movement. And in so doing, I could not gather all of the pieces that were gold-plated. So even though this movement represents the IBM Model 37 movement, the last movement that they built, and also the finest movement, when I say the last movement, I mean the last new model of movement, and the finest movement that they built, I was not able to obtain all the pieces. Now let's look in this opening right here in the bottom section. Depending on the models and the features of the movement, the winding mechanism to wind the mainspring set in this particular position. If the movement was a Model 15 or a Model 17 or a Model 25, certain ones of the Model 25, this had a large electromagnet in here and a ratchet mechanism and a pawl that pulled this ratchet wheel right here to wind the mainspring. We can see the mainspring right in this area. And it was a winding mechanism to go in there. I was unable at the time to locate the pieces for the winding mechanism. This movement is incomplete in that situation. The later Model 25 movements that had some commonality of these parts had a little synchronous motor that was mounted in here, and that synchronous motor had an eccentric that wound the mainspring in this region. Fit right into the same place, same mounting holes and whatnot. The synchronous motor turned, it was a 50-cycle synchronous motor running on 60 cycles, so it ran 6/5 times revolutions per second. And this gave us something like 70 or 72, whatever the number is, pulses a second to wind the mainspring. This winding ratchet here represented minutes. So the mainspring was overwound by about 12 minutes per hour. And back in the back here is a device, an overflow device, so that the mainspring becomes wound and is not overdone. That gives us the ability to recoup from power failures. The mainspring here is good for about 12 to 15 hours, and barring power failures no longer than that, then this would never stop during a power failure. A third type of winding mechanism that went into this was where this was used in the Model 35. The Model 35 had a massive base, somewhat like this, only much larger, and a gear train and an electric motor and a pair of weights. This pair of weights would drive the movement for about 10 to 12 days, and they were wound about every other day. About every 48 hours they were picked up just a bit, and the mechanism was wound through a differential gear system, a sun gear system, and then the movement could withstand much longer power failures. Turning back again to the back side, we can see the train in here. This is the center shaft, what would be the center shaft on all models except the Model 37. This would have been the second wheel. Remember, the mainspring is on the center shaft, so this is the second wheel, and then the escape wheel. This is a 60-beat movement. The industrial aspects of this, we have a little balanced teeter-totter arm right here that's on the verge shaft. It has a 2-gram weight right here on the end, and it's pretty much balanced here. So as the escapement anchor rocks to and fro in the escapement, it lifts this little weight and lowers it onto a contact here. And this contact provided in the industrial system a very accurately timed impulse every 2 seconds. This contact produced 30 pulses per minute and was used for a variety of industrial control items. This arm and the little 2-gram weight that is right here, there's a pair of arms here, and there's a little piece broken from this fiber at this point. And a small cam back here on a section of the gear train that turns 1 revolution per minute. These 2 arms are differential riders that ride on that cam, and that closes this contact for a period of 2 seconds once each minute. So this gives a minute impulse, a very accurate timing in both duration of length and the interval each minute. Off of what would be the center wheel here, and that is not the center shaft in this particular movement, is a pair of cams and a pair of cam riders. These are differential cam riders, and we control two sets of contacts right here. The lower contact is closed for 50 minutes per hour. The upper contact is closed for about 35 seconds per hour. The lower contact is closed from the 00 minute through the 49th minute. The upper contact is closed from about the 59th minute and 10 seconds to about 59th minute and 40 seconds or 45 seconds, or approximately there. The purpose of this contact assembly is that remote clocks, such as tower clocks in the tower of a building, or attendance recording clocks and whatnot, run on a 3-wire circuit, receiving a minute impulse via that 3-wire circuit. And the lower contact sends out 50 pulses per hour. The upper contact sends out about 20 to 25 pulses of an hour in rapid succession at the end of the hour. By the teeter-totter of this arrangement and the teeter-totter of a contact arrangement in the receiving clock, if the clock becomes fast, if for any reason it should be fast, this contact here deducts about 10 minutes per hour until it becomes correctly on time. Remember, this one only closes for about 50 minutes an hour, so it would cause the clock to lose about 10 minutes per hour until correction is made. If it is slow, then it would receive via this contact, the upper one, and the rapid impulse contact would receive about 20 to 25 impulses per hour in rapid succession, which would advance any recipient clock that might be slow. And that's the technique by which remote units were regulated. On the back side, in this area, see if we can get the light in here, we can see a 2-gram weight and another 2-gram weight and a pair of differential arms on cams and here, and a contact set and a contact set here. These were called duration contacts. They were for special features that an established period of duration other than the 2-second impulse could be set up there. That was used in the correction of clocks that had continuous running second hands on them, remote clocks with continuous running second hands. We used a duration here of 6 seconds that functioned to monitor the hourly regulation of the clock, the hourly regulation being that of the minute hand and that of the second hand. And the second set of contacts, which had a duration of 12 seconds, was used to monitor the hour hand and to regulate it. It was called the 24-hour regulation, but in fact it regulated every 12 hours at 6 and at 12. At 6 p.m. and 6 a.m., or in another version of the clock at 12 a.m. and 12 p.m. As we look across the train down here in the front, coming across this train, we find a set of contacts here and 3 straps, and this was used to set up the timing of radio signals, which we built a group of remote indicating clocks that were regulated by radio control. Actually, the radio control is stretching the thought just a little bit, because the real carrier was a carrier current that traveled over the AC power mains. It was a sub-radio frequency that was superimposed on the electric mains. What this did, the first contact at about the 56th minute of the hour, turned the radio transmitter on and readied it for the second contact, which closed in the 58th minute of the hour and opened in the 59th minute of the hour. And during that period of time, the pulses for the radio control was sent out through this with duration lengths, with the length of duration of those pulses coming from the contacts back here that we discussed a little earlier. The movement has a feature of correction. If I pull this solenoid right here, notice that I return the second hand to 0, 0. Let's look at this again. We can see that as I can pull the second hand off time, and either way, and pulling this solenoid will set the second hand back to 0, 0. In this movement, also from the radio control, we turned on a radio receiver, which was built into the clock case. The radio receiver was crystal controlled and pre-tuned to the National Bureau of Standards. The National Bureau of Standards transmits continuously on a variety of frequencies that is quite well known in the communication industry. And this contact would turn on the radio receiver, and it would monitor the time off of the Bureau of Standards, off of the U.S. Bureau of Standards. And through the contacts in the rear and the radio turn-on from this control, from the duration contact back here, we would determine whether or not this movement was on time to the Bureau of Standard down to the second. There is a second's beat that's transmitted by the Bureau of Standards, and it would look to see if this second hand was indeed in step with the National Bureau of Standards. If it was not, and the increments of adjustment are 1 second, if it is not, it would track that for 5 minutes. It would track the Bureau of Standards for 5 minutes and compare that second-hand position. And if the comparison had any error, then at a certain marked time in the Bureau of Standards signal, this solenoid would be pulled quickly and released and carry the hand to 0, 0. The basic movement has the capability of keeping time to about plus or minus 1 second in 4 to 8 days. So it says that this would probably get an adjustment in its absolute coincidence to the National Bureau of Standards about once a week. Yet the radio that was comparing this looked at it every hour. If reception was not satisfactory, it would take a look. It would say, I do not have a valid signal. I do not have an adequate strength signal to compare the validity of it. It would turn off and try again an hour later. All right, let's pause on the tape here for a moment, and then we'll be back and continuing on. The reason for the pause on the tape is that we're approaching the end, and I needed to look and see about how much time was left. I do not have a camera operator here, so I have to do all this myself. Now let's look a little further. We said that the center wheel on most of the IBM movements, or the center shaft, is here. In this particular one, because this has a sweep second hand, the situation is built differently. There is a heavy coaxial shaft coming right out of this central region in here, and that coaxial bushing has the passageway of the second hand coming out. The second hand and its shaft is a lightweight shaft. And then journaled on that is a couple of other features. Here, this right here is the gear that carries the hour hand pipe. Right behind, in behind here, is the gear that carries the minute hand pipe. There is a pipe on the minute hand, for the minute hand, a pipe for the hour hand, because the second hand is in the central section. We say it's coaxial, it's really a triaxial shaft. The gear train that drives the hands comes up from what would be the center wheel. This cam turns 1 revolution per hour, comes up this line, and drives the hands up here. As we look around in the back, this is the beat adjustment mechanism right here. These 2 little thumb screws here, that's one of the nicest beat adjustment devices I've ever seen on a clock, barring none. This is a zero backlash system with a little knurled nut, and you can reach right in behind the dial like this, and when you're servicing it, and make the beat adjustment there. The movement again was brought up from the scrap at the end of well, as a matter of fact, this I gathered this together 2 or 3 or maybe 4 years after IBM had discontinued the business. Let's look at the parts and see where the gold is and where it is not. This is all gold-plated here. This cam is gold-plated. This one is. This gear and this little attachment plate that carries the contact here is not gold. This particular gear is not gold. The one right here is. All this mechanism up in here and all of this plate out here is gold-plated, and the straps on the electrical contacts that carry the screws here is not gold-plated. This bracket all out here is of that material. Now this this movement has been in a box and stored at my place since about something in the order of about 1960, and there's very little tarnish on it. There's a lot of fingerprints, but there's not any significant tarnish except on the parts that are not gold-plated. I had thought that someday that I would be able to find the pieces to set this movement in operation, build a case to put it in, and whatnot. I do have all of the pieces for a synchronous motor winding mechanism that goes in here, with the exception of the field coil. The field coil is a little telecron coil, and it was so popular for so many years that presumably someday I'll be able to locate one of those. But this is what we had in the latter days of IBM and industrial time controls. There was never a great many of these of this particular movement built. It's estimated that there was only about 10,000 of movements of this type that was ever manufactured, because it went into the line not too long before the demise of the business. The basic components that was used in the models 15, the model 17, the model 25, and the model 35, they were built by the hundreds of thousands. As a matter of fact, the model 15 movement dates back into the Depression years in the early 1930s, and the model 17 goes back into the early and mid 1920s. If you have looked at the random clock talk tapes that I have made in time past, one of the tapes, I'm not sure which, it's about tape 3 I believe, has a view of an IBM Master Clock, which is a model 17. This is the Master Clock with the yellow oak case, and that model clock, that model 17, was built in 1928. It has the same basic plate, the plates that are here, and the escape wheel, the escapement anchor, and some of the gear train inside is directly interchangeable into this. It was a very, very fine clock, and I suppose that barring just malicious or accidental damage, that those older master clocks will continue to run for hundreds of years to come. All right, let's, during this pause, I took a look on the tape, and there's only just a very, very few minutes remaining, and we'll just point out a little more of the inside features of this. This is what would be the great wheel. It's really on the 1 revolution per hour shaft. A long, thin mainspring. That mainspring is about 6 feet long. It's about 5/1000ths of an inch thick, and it's about 5/16ths of an inch wide. When you take that mainspring out, it becomes perfectly straight. It's a spring that I've used many of these to make suspension springs from other clocks. I occasionally have a broken one. I would save it for that. It's a very long, very soft mainspring. The ratchet wheel drive. This is the click pawl, right? See if we can get right in here, that retains the mainspring while the winding mechanism is going for the next tube. The shaft that we may be able to see right here. Let me try the eraser of the pencil. That pinion right there is driving the camshaft that gives us our minute impulse and our duration contacts. Out here on the front, we have the Escapement Anchor bridge right here in this area, and we normally would set the anchor bridge in approximately correct position in the back, and final adjustment would be made on the front. There are a few features on this that are yet missing. Off of this gear right here, which is associated with the hour hand and makes 1 revolution in 12 hours, right in here is a cam that had a differential rider on it, and in a couple of holes that's in the movement, right behind this little spring right here, stood a plate with another contact assembly. And that's where we got the information, gathered the information to supervise the hour hand position of remote clocks. That piece I do not have. There was also in these holes right here in the top another plate and a cam rider that rode this in a different place for another piece of industrial control. The holes down here in this had bushings in those holes, and if the movement was wound, if the winding mechanism was an impulse wind, then the lead wires feeding that magnet arrived at that point. These these holes here, this whole pair of holes and the pair down here, and this hole is there to key in dowel pins for the winding mechanism. There's another dowel pin hole over here in this area for the same purpose. This was a peephole to look through to see the adjustment of some of the winding mechanism. Looking in the back, there is a feature here that is broken but repairable if it should be. This stud coming right out here is broken off. Now, when I pull the solenoid right here, that stud worked a little lever which is tipped over. That lever is right here. The purpose of that lever, when we pull that solenoid and do that, we had a feeler that went in to the escape wheel, grabbed the escape wheel, and held that wheel with its teeth clear of the escapement pallets and locked it in position while the hand is being positioned here so that there could be no damage on the escape wheel teeth in the correction operation. Well, so much for what has transpired in IBM in the past. In all probability, you'll never see another one of these movements, and I suspect that neither will I. This is one that was saved from the scrap right in the end period of time. I gathered the pieces together on this as a memento in about 1960 or 1961. Thank you for being with me today. My name is J.M. Huckabee. I'm located on the J.B. Ranch, just outside of north side of Austin, Texas. I'm a certified master watchmaker by the American Watchmakers Institute, a fellow of the British Horological Institute, and a retired IBM engineer. And we're doing this for fun in the good life of retirement. Thank you for being with me. Continuing Random Clock Talk by J.M. Huckabee, let's look at an unusual industrial timepiece or an industrial movement built by IBM. This movement was called the 90 Series and was manufactured from around late 1946 through the end of 1958. These were built by hundreds of thousands. The purpose of this movement is to supply time control for a variety of other equipment that IBM manufactured. Among these items were attendance recorders, job time recording equipment, production recording devices, institutional equipment for hospitals, schools, and things like tower clocks, the clocks that's in the tall steeple towers, and the like. Its purpose was to provide a very accurate minute impulse, that is, an electrical impulse each minute, plus various other controls for measurements for auditing and the like. This movement has a similarity to the old Seth Thomas number 10. If we take a look right in this area and the balance wheel, we might mistake it for the Seth Thomas number 10. A closer inspection will show that that is not the case, and it also has a similarity to the Lux movement. There was a Lux movement that was built in the same era of the Seth Thomas number 10. Has a similarity to that, but neither is it a likeness of the Lux movement. As we look at features on front here, this is the minute hand shaft, the hour hand shaft, and the gearing we see here is the motion work for the dial. And in the industrial application, many of these were built without an hour hand and without the motion work. It just simply had a little stub minute hand and a ring, a skeleton ring here. That was done in order to avoid the federal excise tax that was on jewelry, which also included clocks in the World War II era and the years immediately following. On the frame of the movement, we have the extension of this phenolic board here carrying a pair of contacts. This contact sends out a 2-second impulse once each minute. The weight here is a 10-gram weight with a differential rider on a cam, the camshaft operating, rotating 1 revolution per minute. This cam and the associated contacts was used as an auditing circuit for remote indicating clocks, and as such, they could detect, the master movement could detect whether or not the remote indicating clock was either fast or slow and make corrective action accordingly. Mainspring barrel. This mainspring barrel has about something like 2.5 days of running time of spring capacity. Turning to the back side, we begin to see things that look different from conventional clockwork. Here is a large electromagnet, and it was called the differential clutch magnet. When power is applied, this magnet is energized, and from the backside, looking right in this area, we'll see that a little crown wheel is engaged with a pinion right here. You can see this motion happening right there. The crossbar carrying the pinion rotates 1 revolution in 8.5 minutes, and if power is applied, the crown wheel is engaged with the pinion, and the pinion rolls around the crown wheel. Looking a little further, if we rotate the crown wheel, we find that it moves the regulator on the movement. This is the regulator arm, and the regulator arm has a traveling curb slot that follows on the hairspring for regulation. Rotating this moves the regulator. However, when the regulator reaches its extreme position in either direction, there is a friction clutch that permits the crown wheel to continue without any further stress on the regulator arm. Now, this is an interesting situation, and it's really the reason that I'm showing this movement on the tape, because it's such an unusual type of movement. This movement is automatically regulated. IBM marketed the device with a statement that it would keep time within 1/2 minute per year. That's before quartz movements, and when we look at what appears to be a crude little balance wheel movement, that is an astounding degree of accuracy. The movement is really much better constructed than it might imply on first appearance. The balance is jeweled. It is not temperature compensated. It does have the flat hairspring. That is, it's not an overcoil type of hairspring. And the secret of this high degree of accuracy is that this mechanism on the regulator here is a differential gear, half of which is removed at this moment. There is a second crown wheel that meshes into this group, and a train travels from there to a synchronous motor. Consequently, the rate of the spring-driven movement is constantly being compared to the rate of a synchronous motor, and the error, if there be any, is applied back to the regulator. Consequently, the movement is regulated to parallel the rate of the synchronous motor. This assures us that we have the same timekeeping accuracy as a synchronous motor electric clock would have. Now, when we have a power failure, this differential clutch is released, separating the mesh of the differential system, and in behind here is a brake. This regulator has a brake applied to it so that it will not move from the position that it was in at the moment before the power failure. The movement continues on, operating from its mainspring, and provided power failures are not approaching the extent of the limit of the mainspring, then when power comes back on, we're still on rate, and we're clutched back in, and we pick up and follow on again. Now, let's look into this wheel here. This wheel, the steel one, is the winding mechanism. This travels into the arbor of the mainspring barrel and winds the spring. There is a ratchet and click behind here, and this can be wound by hand like that if you so like. And the movement is always kept wound essentially full. There is an overflow mechanism in the winding, and that permits to recoup from lost time during power failure, and brings the spring up to essentially full wind, and then the excess winding rate overflows. It's the same principle as the mechanical auto-wind wristwatch. However, the mainspring does not have the bridle and the torque limiter inside the mainspring barrel. The torque limiting mechanism is external to the movement. So this is what the movement looks like at this point. I have the back frame separated from the movement, and we'll take a little study of the back frame, and then later we'll assemble the two sections together and see how it makes a complete unit. This is a dial plate. If we have a full dial on this plate mounts on the pillars, and then the dial mounts over that. So let's pause on the camera, and I'll pick up the back frame of the movement, and we'll take a little look at that. Here we're looking at the back frame. The movement we saw a little earlier mounts on these four bosses, and then there is a pillar that goes into this location. Here is the second crown wheel of the differential system, and right in this area, this is a little Telecron 1 revolution per minute sealed synchronous motor. When I say sealed, I'm talking about the rotor, and the gearbox is sealed in a capsule. The shaft goes out the rear side and makes 1 revolution per minute. As we look on the back side, this is the shaft of the synchronous motor, and we drive up this train, and at this shaft we pass through to the crown wheel on the front side that makes the second element of the differential for the regulation. Now let's look on the back side again. Here we have a second synchronous motor, identical to the one that's on the front side. This motor shaft passes through, and here we have an outrigger with a stud on it and a bronze bushing, and we carry a heart-shaped cam. This heart-shaped cam has a differential between its rise and fall of about almost 2/10 of an inch. Running on the cam is, see if we can get in the picture a little better here, is a little ball-bearing roller, a very hard surfaced ball-bearing roller, and that roller is attached to a lever arm. This lever arm. Now, the lever arm oscillates outward and back about approximately 2/10 of an inch at the rate of once each minute. The arm and the cam rider roller is held in contact with the cam with this spring. Now, carried on this arm and underneath this spring, possibly we can see it if we move this out, is a little indexing pawl. The pawl is identical to this one. This is a little indexing pawl that we might call over in the clock movement, call it a click pawl. And that pawl ratchets this gear. This is a ratchet wheel, and we can see the ratchet motion there. Once each minute we ratchet this forward 1 tooth. And the check pawl here, the detainer, holds the position we're in while the arm goes for a second position. Now here's the principle of the overflow mechanism. In this region, we have an anchor for the spring, and there is a slot in a crescent cut out in this anchor, and by loosening the screw we can adjust the position of that spring anchor, consequently the tension of this coil spring. Now, the principle of the overflow mechanism is such that we leave this gear, this pinion here, and continue on into the steel wheel that we saw on the backside of the movement. That is, the backside of the movement as we first looked at it, not the backside of this piece. And we drive that wheel to wind the mainspring. We set the position of this stud, or this anchor point here, such that as the mainspring approaches full wind, this spring cannot wind anymore. We cannot wind the mainspring any tighter than the tension of this spring that this spring calls for. So what will happen, this arm will be cammed outward, and it will begin to return, but it cannot follow the cam down to the depth of the heart. And that's where we set the level of wind on the mainspring. A very, very functional winding mechanism. The movement, the entire system suffers from one of the same problems that we have in the mechanical auto-wind watch. If a person wears this watch day and night, every day of the week, the mainspring will remain essentially fully wound all of the time. And in long periods of time, as lubricant deteriorates, we may find that the turns of the spring adhere to each other. It really is well if the spring gets wound up and down over a fairly wide range quite frequently. And consequently, it improves the function in this mainspring if you have an occasional power failure and get away from this one constant level of wind in the movement. All right? As we look at this, this is a zinc die casting base plate. The power cord here comes in to power this motor, powers the motor on the back, and on some terminals in this region we have leads that rise up to the differential clutch. So let's pause here a moment on the camera, and I will get the movement, which we looked at first, assembled onto this, and we'll see what it looks like in its entirety. We now have the movement assembled to the back frame, and we have the power applied, and possibly you can see this pinion turning very slowly. It's turning 1 revolution per minute, and this contact right here, riding the little phenolic wheel, is sending out 30 2-second impulses per minute. That's not exactly right. It sends out 30 impulses per minute, with it being approximately equal time on and off. That is, the contacts closed approximately a second and open a second. And that was used, the rapid impulse, as we termed it, was used to correct remote indicating devices that may have dropped a few minutes of time as a result of power failure. That could be sensed through the contact assemblies here and switched to the rapid impulse and recoup the lost time. As we look around to the edge, we see the gear train coming from the winding motor, the winding arm, through the gear train to the steel wheel here, and that winds the mainspring. Now, the gear train in this winding mechanism is such that it winds at the rate of about 72 minutes of running time per hour. That is, the marine escapement here, the balance wheel escapement, is letting the mainspring down at the rate of 60 minutes per hour. The winding mechanism is winding into that mainspring at the rate of about 72 minutes per hour. What this says is that we slowly rewind the mainspring after we've had a power failure, and we gain back the lost time at the rate of about 12 minutes an hour until the lost winding has been recovered. And when that is recovered, then we begin to overflow. If we should approach one of these to give it an inspection, say, is things working all right, we would expect to see this overflowing at the rate of about 12 minutes per hour. And that says that about once every 5 minutes, if we observe this mechanism here, we would find that the arm would not return to the depth of the heart cam, and we would observe the overflow. Now let's turn our attention to the regulator, and let me see if I can get this regulator so that we can see it in the camera. This is the tip of the regulator right there. Let me turn. I'm not sure that we will be able to see that real well. I want to show you one of the functions here. I'm going to take the eraser of this pencil and touch it down to the balance wheel. Now, if I stop the balance wheel at an automatic regulating system, what would we expect to happen? Well, the movement would have stopped. We would expect it to immediately say, go faster, go faster. And that's exactly what we'll see. Watch this. Now, fast is to the right. Fast is to my right. So let's touch down here. Can you see the regulator moving in the rightward direction? Right about there, it has reached the limit. Now let's pull it back. We can move the regulator. Remember, we said we have a slip clutch or a torque limiter in the differential system. And let's stop the balance again and watch it. You see the regulator is headed for the fast position. All right, if we had the regulator all the way over here, now if you'll observe that, and this will move very slowly during the course of some of the conversation here, we'll find that regulator will begin to work its way back to the midsection. To those of you that may have viewed some of the random clock talk tapes on vibrating hairsprings, the balance wheel and hairspring that I was vibrating in those tapes is indeed from this particular movement. I have done that, I suppose 1,000 times in time past. In the earlier years that IBM built these, and remember they manufactured them by the hundreds of thousands, and the bread of life in my household in the late 1940s and through the 1950s was servicing these movements. Many other items of IBM, but this was one of the very, very common. You would do something to some of these every day of the world. And these movements, there is not a piece or a function or a part in these that I can't just close my eyes and photographically see every function and every detail of what goes on. But in the early days, we received the hairsprings and the balance wheels as separate items. Where it is, we got both hairsprings and we got both balance wheels. We place them on the movement, we'd have to vibrate the spring. And that's the reason that you saw in the hairspring vibrating tapes, in about 5 minutes I could put one of these springs within 15 or 20 minutes or so per day in a simple vibrating technique. And the automatic regulator then brought you down to the exact time on it. One of the things that you would do in servicing one of these, the instant you would remove the dial, the first thing you would do, you would look to see where the regulator was located. If it was approximately mid-region, the movement's keeping time. That's the way it is. You would push it all the way to the fast side, and within a few minutes, if it began to work its way to the slow direction, then it was okay. If you push it to the slow side and it began to work its way to the fast direction, then you know that your movement is on time. This is moved back just a little bit, working into the slow direction. We had moved all the way to the fast side. In the early days of these movements, and this is one of the early units, we did not have bushings in the plates. This is about half-hard leaded brass, and over a period of time they would begin to wear, particularly the rear pivot on the second-hand shaft. And on that particular shaft, the pinion is right against the back plate. Consequently, most of the stress on that pivot is, or on that shaft, is at the rear pivot. The pivot is also quite small. So that was one of the major wear points. I have bushed hundreds of these by techniques that you have seen in the some of the previous Clock Talk tapes, and that is the period of time that I become grounded in using hard bronze stock for bushings. The later versions of these, which looked similar, that is the IBM equipment, the model was the same, had inserted bronze bushings in them as they were manufactured. This plate is one of the older ones. It does not have the bushings in it. When IBM discontinued the time equipment division, in the scrap and whatnot, I could have had half a dozen of these things just for the asking. But as it turned out, we seemed to never realize that we might want something until it's entirely too late. About 25 years later, I went through all the scrap of all my friends and people that had saved pieces here and there, and was able to get this movement together. It's not complete in its entirety because certain versions of it had a contact plate out here. Other versions had a contact plate down at the bottom, and still others had a contact plate up at the top. It depended on what the ultimate application would be. This movement is the basic simple movement that might be used to control remote attendance time recorders, tower clocks, or the like. It simply has the impulse self-regulating contacts. It has the minute impulse contact, and it has the rapid impulse contact on the back. That is the only contact group that is necessary if this is to control, let's say, a clock in a steeple tower. So that's about the way the IBM Model 90 movement looked. This movement is a very, very fine timekeeper. It was inexpensive to manufacture. It met a competitive market. And in the period of time that it was built, there was nothing in the American market that would approach it in timekeeping accuracy and recovery from power failures as this one would. Of course, by today's quartz movement standards, we look at this, well, it's industrially speaking, it is classified as the kitchen clock would be in the household clocks. An interesting curio, but of no commercial value. Looking at this, we can see this regulator is continuing to work its way back to the central position. In gathering this unit together from the scrap after so many years, there was quite a number of problems in locating all of the pieces. As a matter of fact, the rear plate that's on this movement was salvaged from an entirely different model of mechanism. There's some peepholes or portholes in the back of this that are about as large as, about the size of your little fingernail. And one of those holes is exactly in the position that the escape wheel pivot had to occupy. So when I put this together, we had to place a bushing in that plate back there that was about 5/16 of an inch in diameter, and locate a pivot hole for that. Also in the crown wheels in the differential mechanism, I had a problem in that. I had two of the crown wheels for the near side and none for the far side. So we had to remove the regulator arm from the second one, make a new shaft for it, make the bushing that goes with it, and things of the like. But all over this movement, I had to make many pieces in order to bring it back to its complete function. As a matter of fact, this wheel and hour hand pipe had to be handmade. There's a number of variations of the contact assemblies that's used on the movement, and when we have the outrigger here, this train continues on out to this side. If we have contacts down here, the train continues down. And if it is up here, we have a continuation of the train in the upward direction. It turns out that the pieces that I had available just did not make up the entirety of the movement, and I had to make some of the wheels there. Now, let's ask the question, what value is this movement today? And the answer is really, it has no value at all, except it's just an interesting curio. If we're purely interested in timekeeping, we would get that off of a quartz-type movement. If we need minute impulses, we would simply get that from a quartz movement with an electronic subdivider of the impulses, so that we'd get the minute impulse direct. And how technology has changed the times. Here is a pair of hands that I have located, that original IBM hands. They're not the hands that was used on this movement, but they are compatible to it. These hands were from the Model 25 Pendulum movement, and the Model 25 Pendulum movement had some of the same gear train on it as this Model 90 movement. So these hands will fit the movement, but they are not original in type. If you hear some thumping going on in the background, and you will hear that on a number of these Clock Talk tapes, that is an IBM Pendulum type Master Clock, a Model 17, which is here in the shop. And the thumping that you hear going on is the rapid impulse relay, which was used to correct remote units that might have lost time due to power failure during the previous hour period. It also sends out an impulse once a minute, which we hear as a thump on that relay. This Model 17 clock was built in 1928. It's one that I purchased that had been replaced in school. and I've had this clock since around the mid-1950s, and that's what the thumping noise is in the was in the background. Thank you for being with me this morning. I'm J.M. Huckabee. I'm a certified master clockmaker, certified by the American Watchmakers Institute. I'm a fellow of the British Horological Institute, and I'm retired. Retired on the J.B. Ranch on the near outskirts of Austin, Texas. It's a beautiful day here in Texas today. There's some fleece-like clouds all over the sky. It's moderately cool. It's about 80 degrees here right now. The time is just about 9 o'clock. 9 o'clock a.m. We started in the shop here about 7 o'clock this morning. The temperature was 70 degrees. We had a little rain shower last night, for which we are very thankful. Cooled things off. This is the 5th day of July, 1988. Yesterday, the 4th of July, the power failure here brought intense heat. The air conditioning was off, and our water was off and whatnot. We had a good day yesterday. The outside temperature reached 100, and today is a real relief. Thank you again for being with me, and I trust that through these tapes that other workmen that have interest in various and sundry types of clock making, clock repairs, and whatnot will be able to profit from some of my experiences.